First one is by Saso Grozdanov. You can see the slide.
Thank you. Thank you guys for organizing this. It's wonderful being here. First time, actually. Not first time in Florence, but first time at GGI, so thank you very much. Okay, so the title of the talk is Spectral Duality Relation in Thermal Field Theories. So what do I want to talk about? Well, this is a slide of things I want to talk about. Things like plasmas, let's say in the sun, maybe things like, a neutron star, quark gluon plasma. I will not really directly say anything about this. I will talk, let's say, generically about thermal quantum field theories, which is a sort of an underlying topic of all of these. Can you hear me okay, actually? Yeah, I don't know. Yeah, which is an underlying topic behind all of these things. So, I will just generically talk about, let's say, thermal field theories. And let's say these thermal field theories are specified by two parameters, okay, like a gauge theory. So there's some kind of number of colors, NC. There's a coupling constant. And now, what are we going to do? So, of course, at weak coupling, you would be at, somewhere here in this phase diagram. And the typical techniques you would use here would be kinetic theory and perturbative QFT. You heard some of this work last week from Alexander Soloviev, who's not here anymore. And I guess most of you were not here, so that's a shame. Now, today I will mostly discuss thermal field theories from the holographic point of view. So most of what I will say will, unfortunately be somewhere here in the large N regime. Most of it will be at very, very strong coupling, although I think various things I say are also true at, intermediate coupling. I will tell you what I'm, what is where. So of course, via holography, which, I assume that most of you at least sort of know how it works, is where you use techniques from black holes to say things about thermal physics. Okay, so what do I want to talk about? I want to talk about spectra. I like discussing spectra because they're sort of, generic observables, the kind of thing that tells you what your quantum field theory is doing. So let's start with a very simple thing. So this is a spectrum of some simple zero temperature quantum field theory taken from Peskin and Schroeder. You have some correlation function of, let's say, basic operators, phi, scalar theory. There's some numerator, there's some denominator, okay? In momentum space at zero temperature, zero chemical potential, this is relativistically invariant, so you can plot the spectrum as a function of p squared. So what does that look like? Well, there's some poles. For example, there's an isolated pole that corresponds to the physical excitation of the field at m squared. Then there's some poles coming from bound states. That's what they teach you. These are sort of hard to find generically in quantum field theories. And then they tell you there's some cut. Okay, there's a cut that starts at this threshold of 2m squared. Okay, so this is a typical picture of a spectrum that you expect from at least perturbation theory. So my question is, what does this look like for a generic quantum field theory at finite temperature? So at finite temperature, this is a much, much more difficult question. First of all, Lorentz invariance is broken, right? By temperature, you break boosts. So everything I do will have this broken Lorentz invariance. So for these reasons, I will, all of my operators will be functions of omega and q, omega being frequency, q being spatial momentum. And typically, I will be interested in conserved operators. So correlation functions of conserved operators, one reason being that these are, nice to compute from holography. Another reason being that they, in thermal things, they teach us a lot about the infrared, which is hydrodynamics and so on, okay? Good, so what does the spectrum look like? Well, this is a difficult question. So what we know is that at zero coupling, the spectrum has an infinite sequence of cuts. This is coming from a calculation of Hartnell and Kumar. If you go to strong coupling, at least in the large N limit, then holography teaches you from many, many calculations that the spectrum, so here I'm plotting the complex omega plane, dots are placed where there's a pole of the correlator, or in other words, where A, this denominator is equal to 0, okay? So in holography, so what is coming from black hole calculations, you always find, at finite temperature, you always find a meromorphic spectrum. So what this means is that the spectrum is made of simple poles, okay? So the correlation function is meromorphic. Okay, now, so what is the structure of these correlators in, generic QFTs, so they can be computed from the method of quasi-normal modes via holography. If you don't know how this works, just think of it as, there's some prescription, black box prescription, which tells you that in certain quantum field theories, there's a dual description in terms of a black hole. And the spectrum of the black hole ring down will tell you about the spectrum of your dual correlation function. So doing these things in generic QFT is very difficult, right? So this is one of the reasons why we like holography. So let's say you want to do this kind of calculation in kinetic theory. What you have to do is solve these horrendous collision integrals, right? So this is very difficult. In perturbative QFT, you have to, calculate even to leading order and usually an infinite resummation of diagrams. So this is also very difficult to do. So one of the reasons why we like holography is because there, at least in the large n limit, right? So large n is a semi-classical limit, so holography is the nicest representation of what classical means here. Well, the duality transforms to a classical field theory, but it's gravity, but okay, it's still a classical theory. So in holography, to get these results, what you need to do is solve differential equations, okay? Which is much, much simpler than anything you do in QFT. So, in QFT, even if you go to the large n limit, even if you know that this is a semi-classical limit, for a typical QFT, you will still need to do an extremely difficult calculation. So holography is kind of a magical transformation to variables where everything is just classical. Okay, good. So this is why, yes? Sorry? Yes. It's just it's a free theory. All these cuts are coming from just the thermal distribution function. Yeah, they're coming from these cautious of things with 4 pi's and things like that. Yeah, exactly. Okay, good. So what I want to tell you about today is the spectra and somehow the special role that the hydrodynamics plays in it. So what is hydrodynamics? Well, this is not the audience I need to say too much to. Probably most of you know more about hydrodynamics than I do. So hydrodynamics is a theory of conserved operators, of things that are, long-lived excitations. So, for me, you can think of the conservation of the energy momentum as the equation of motion. And, you can write down some hydrodynamic theory, which is a gradient expansion. And because I will be looking at two-point functions throughout my talk, it's sufficient to analyze linearized hydro. So, a nice sort of measurable thing in linearized hydro are dispersion relations. So in particular, I will be discussing a lot these dispersion relations, which are solutions to the conservation of T mu nu, omega as a function of Q expanded as a power series in Q, okay? Now, first important lesson is that generically these things are infinite series, okay? Because hydrodynamics is in principle an infinite order expansion. I'm looking at large n. Right, so the dispersion relation of the hydrodynamic mode can be represented as an infinite series that looks like this, okay? Now, if you go to our favorite examples, the specific examples that are contained in standard classical hydro, this would be a diffusive dispersion relation. Omega goes as Q squared. This is sound. There's a real part due to propagation. It goes as Q. And there's an attenuated part that goes as Q squared. Okay, that's imaginary. So what is this in terms of my pictures of the spectra? This is the lowest lying mode, the mode that's closest to the origin. Okay, this is the hydrodynamic mode. And this is a typical spectrum with diffusion. There's a diffusive mode on the imaginary axis for real Q. And then there's this Christmas tree that Pavel was also mentioning yesterday. Okay? Okay, so as a small aside, before we get to the main things, one can ask, what is the analytic structure of hydrodynamics itself? Okay, so of course, the obvious answer is that if you only have a hydrodynamic theory, at classical level, you have a pole, right? So it's a meromorphic function. You will have a pole here. This corresponds to the diffusive pole. So one interesting lesson from writing down an effective field theory for hydrodynamics in this Schwinger-Keldysh language, if you do this, then you can compute loops. So one interesting thing to keep in mind is that with these loops, okay, the hydro loops, with every next order, you actually accumulate a new branch cut. So the generic picture of what happens for a diffusive mode is the following. So your theory will have a pole at omega is equal to minus IDQ squared, okay? And then you will have an infinite sequence of branch points, which lie at omega equals to 1 minus idq squared over n plus 1. So these branch points, you see, so there the pole is here. Actually, in some dimensions, this pole splits, and it attains a real part. At least in low dimensions, this is reliable. In higher dimensions, it's not entirely clear what exactly is going on because higher correction might kick in. Well, the lesson here is that there's a pole, like always, and then there's an infinite sequence of branch points, okay? Each next loop calculation will bring you a new branch point. So one loop correction would be responsible for the usual long time tails. And these are then, subsequent corrections to the usual long time tails. You can calculate dispersion relations, all these kinds of things at higher loops. Everything is extremely non-analytic, okay? That's the generic picture you learn from hydroeffective theory. We computed this, at least in the sector of what are called the banana diagrams. So you can see that at each loop, you have a diagram that looks like this, right? So the picture is consistent with what you expect from QFT. So there's a diffusive mode. There's a loop diagram. It splits into some number of virtual particles, and the splitting will create a new a branch point. So each one of these at higher and higher orders corresponds to a new branch point, okay? Anyway, this is just some lesson, I think, to keep in mind. I think the generic lesson is perturbation theory creates branch cuts, okay? Right, so how about not perturbation theory? So how do you go from the picture of an infinite sequence of cuts, this is completely reliable, this is a free field theory exact calculation, to something that looks like this, okay? As you tune the coupling constant, let's stick to large N, okay? How do you go from one to another? Well, it's an interesting open question, okay? So one could attempt this from the weakly coupled to the strongly coupled side, and then you can, for example, do kinetic theory. This is exactly what Alex discussed last week. The generic picture there is that you have cuts and poles. So you have poles corresponding to hydrodynamics, to certain quasi-hydrodynamic modes, and there are also cuts corresponding to, so this is computed in RTA. This is something going beyond RTA. In any case, it's a combination of poles and cuts, okay? So now, let's just go just to holography. So when you do just holographic calculations, you never see cuts, okay? At least at finite temperatures. You always see poles, so these isolated excitations. Okay, so you could go, for example, from strong coupling towards weak coupling. This can be done to some degree by using higher derivative supergravity theories. So in the holographic dictionary, the alpha prime of string theory, the string tension, is related to the dual coupling constant, lambda. So you can have a perturbative series in supergravity, and from that you can figure out what inverse coupling constant corrections to some degree are doing to the spectrum. Well, the lesson there is that you always have poles, okay? Just always have poles. And what they do is, as you go towards weaker and weaker coupling, they do the correct thing in the following sense. So let's say this is at some very strong coupling, and this is at weaker coupling. So these poles will come closer and closer and closer together. In fact, they're interlaced with zeros of the correlator. So there's always a zero in between two poles. We now actually know that this must always be true. We can prove this generically for any correlator. So the picture is always that you have pole zero, pole zero, pole zero. As you go to weaker coupling, they come closer and closer together. Their residues go to zero. And in the limit of pole zero coming infinitesimally close together with residues going to zero, you create a branch cut, okay? That's how this works. And you can see this explicitly from holography, how this is done. So, okay, good. So then, of course, you may ask, well, what about these higher branches, okay, of the cuts? And here, it's not entirely clear. So what we've managed to do so far is have a toy model of, you can add higher and higher derivatives to your supergravity, and you can study this. So if you go to a theory with higher and higher derivatives, one can cook up a model where you essentially create a spectrum with not only one Christmas tree branch, but a secondary Christmas tree, okay? So perhaps one way that this actually works is that at very, very strong coupling, you just have the Christmas tree. Then as you start tuning the coupling, what happens is that the poles come up the imaginary axis. Then they start pairwise colliding. They move off the axis. They create several branches of the Christmas tree. And then as the coupling goes to zero, they all stretch out and create a cut. This is the picture. This is the best that I can do with all the evidence of creating a picture. But getting this is very, very difficult because, it's various perturbative calculations on various sides. I should like to point out that this picture of having just poles in thermal theories is supported by a very nice recent calculation by Matthew Dodelson, who is a postdoc now at Harvard. He studied the SYK model. So this is a 0+ dimensional QFT. It presumably has some holographic dual, but the calculation has nothing to do with holography. He just took the field theory and studied it numerically at finite coupling. Okay, so he varied the number of fermions, varied coupling, things like this. And the picture there was consistent with holography in the sense that there were no cuts. Okay, he numerically found only poles at any coupling. So, okay, so this is the first part of my lesson that, generically at finite temperature, non-perturbatively, I expect poles. Or of course, there's no proof that, in QCD at finite coupling, there aren't cuts as well. So I'm not going to, so for just to set the stage, for the rest of everything I say, I will only consider spectra which are meromorphic functions, okay, which have only poles for the rest of the talk, if that's true or not. Okay, Pavel. This one? It's very bottom up. So it's Einstein-Hilbert plus Riemann squared plus Riemann to the 3. Each with an independent coupling, it was that. So basically, we just started adding higher derivative Riemann tensor corrections. Yeah. Yeah, so it was, the question was, what can happen? And this can happen, okay? Now, is this reality? I don't know. It's a bottom up. Yeah, because it's a perturbative calculation. Well, I mean, it's a perturbation theory on top of a non-perturbative mode, if you like. No. Yeah. Well, no, because various things could happen when you resum all these cuts. That's something we've not been able to do, for example, because we don't have all the diagrams. We can just show that at each loop, there will be a presence of a new cut. It's possible that once you resum all of these cuts, something will happen. That's one possibility. I don't know. Yeah, you're right. So what I guess one should do is take stochastic hydro and just numerically compute the spectrum and get the full result. And I mean, I'm looking at both of you there. Maybe you've done this that I don't know. I think it matters because they give you non-analyticities, like long time tails come from a cut, effectively. No. Well, at least order by order. So order by order, I agree. The question is what happens when you resum it and set n equals to 16? That's the question. I don't know. I mean, but yeah, I mean, pole's not the same as a cut, right? So let's say you yeah. So let me give you one example. Let's take your calculation of n equals to 4 spectral function, okay? You did it at infinite coupling. So of course, at zero temperature, infinite so let's forget the coupling. So there we can discuss about temperature. So at zero temperature, we know from a CFT that there's a cut. Yeah? So the spectral function is smooth. If you just look at the spectral function, it's smooth and it goes up. So then, for example, if you add coupling constant corrections to this, so what this will do, so as these poles come closer and closer to the axis, for example, for a very long period of time, you have these bumps. So you have the bumps, they look like quasi-particles. They get narrower and narrower, and their residues go down, and eventually they melt into this continuum of the CFT. That's what I would say is the difference, okay? Now, so I would say that as long as you have poles that are close to the axis, I would venture and call this a quasi-particle. And when you have a cut, there's no quasi-particles. It's just a continuum of decay, of possible decay modes. Like in a CFT. I don't know if this is a good answer, but that's how I think of it. Yeah, yeah. So for a while, they look like delta functions, and then they vanish into this continuum. So we did this with higher derivative. This is a paper with Andrei Starinets and Jorge Casalderay Solana. You can see the spectral function going from a wavy thing to a continuum, which kind of shows physically, I think, how this melting of poles into a cut works. That's the best I can do. Yeah, very good. Yeah, Pavel, at every order of n, there will be cuts, yeah. So my question is, a resummation. And this is numerics. This is a numerical calculation at some, let's say, finite n, okay? And it has poles. Of course, this is a zero-dimensional theory, so I don't know. But I'm just opening this question because I don't think, this is not a resolved problem as far as I'm concerned. Of course. Yeah. So this is not, this is an effective theory to only leading order and derivatives, but to all loops. Yes, some no. Some yes, some no, yes. That's why as I said, some of the results are unreliable in high dimensions because of the way these extra things enter. But for those bananas, what you will get is basically something like k squared log squared, k squared log to the third. You get a series of powers of logs, and God knows what happens. So this is like a 1 over n expansion, what I would say. More like the coupling constant expansion, okay? This is just my introduction. This is nothing, yeah. Yeah, so yeah, but that's okay. It's a very modular talk. We can stop at any point. Okay, main outline of my talk. I hoped, so the first part is to convince you that looking at meromorphic functions is okay, even though Peskin and Schroeder show you a cut. Now the second part is sort of the new things, some of old stuff, some of new stuff, of how extremely constrained these spectra are in holography, okay? And of course, via holography, it's also, these are just statements about black holes, which, I'm very interested in. So this first part, this is now very well known, but I just have to state it. So just the statement is the following to keep in mind. So these hydrodynamic series, as I told you, are some power series in Q. For shear, for diffusion, there's power series in Q squared. For sound, they come in pair, and their power series in Q squared to the n over 2. It doesn't matter. What matters is that they have a finite radius of convergence. So if you plot the analytic structure of omega as a function of, let's say, Q squared, and this is a real plot for n equals to 4 super Young-Mills. So for any such theory, under, I guess, mild assumptions, you will have always a holomorphic disk. So that's a very important statement, that these dispersion relations as a power series in Q converge. Okay, I will use this a lot. They converge. This means that there's some disk where this function is holomorphic. And then outside of this disk, there's all sorts of horrible stuff happening. There are all sorts of cuts, and all of these cuts, for example, will happen due to collisions of the hydrodynamic mode in the spectrum with something else. Okay? When you have a non-trivial collision, you have level crossing. This is an old story. That's why I don't want to talk about this too much. But the spectrum, the analytic structure is holomorphic. Anyway, so that's the important statement. So, for example, you can go to holography. You can compute the radius of convergence of the hydrodynamic mode. This is, for example, the plot of n equals to 4, super Young-Mills, dispersion relation, diffusive hydrodynamic mode as a function of the inverse coupling. Okay, you can do these kinds of calculations from holography. Now, that doesn't matter. So the first part of all I want to say is that this, in these holographic spectra, what happens is that all of these modes, so all of the poles, in sufficiently complicated theories, have an intricate sort of interplay between them. So what can happen is, and what does happen generically, I would say in the majority of such interesting theories, is that these, at somewhere in the complexified momentum space, oh yes? It depends on the model. It's theory dependent, model dependent. There's no generic answer. Yeah. It's finite. That's all I want to say, is this is finite. It converges, okay? Who knows? No idea. I mean, a generic QFT will not allow a classical hydrodynamic infinite derivative expansion. So that's already the first problem. Maybe in a generic large N QFT, this is true. Maybe. Yeah, probably yes. I would conjecture a yes statement to that in the large N limit. Good. So the point is that basically, the statement, if you know the full dispersion relation of one of the modes, you can get the dispersion relations of all of the other modes. Okay? This you can show in explicit examples using various methods. For example, one thing we developed was an algorithm using some complex analysis. There's a Puiseux theorem and combined with what is called the Darboux theorem. Essentially, the way this works is as follows. So you have a hydrodynamic dispersion relation. This is this guy. It has a finite radius of convergence, and by hydrodynamics, you know the series expansion around the origin. Okay? Now you know that it has a finite radius of convergence. Then you can use an adaptation of what is called the Darboux theorem that the details are not important, they're in papers. So what it means is that you find that this thing has a finite radius of convergence, and using this Darboux theorem, you can find where the convergence dies. So you can find the location of the nearest branch point, and you can find the order of singularity. Okay? Now you found this, and then this Darboux theorem will help you re-expand your function around branch point singularity. Okay? This can be done explicitly. Well, I mean, if you know all of the terms, you can do it, of course, exactly. Otherwise, you have to do it numerically. But this can be done. So what this means is now you've expanded the hydrodynamic mode in the frequency space as a function of Q around the branch point. And the meaning of this branch point, as I told you, it's a place where the hydro mode collides with another mode. Okay? So now, by using Puiseux theorem, which is essentially saying that if you have a singularity that goes like a square root, there's a plus and a minus. So you can use these theorems then to figure out the second branch of the function. So at each branch point, there's a Riemann surface in the dispersion relation. So from the re-expansion of the hydro mode, you can find the dispersion relation of the second mode. So you can find the dispersion relation of this mode expanded somewhere in the complexified Q space here, okay? So now you have the dispersion relation of this mode, and then you can do analytic continuations again. Then you go to the next one, the next one, and the next one, and the next one, okay? Assuming that they all have non-trivial level crossings among them, you can find all of the dispersion relations in the spectrum. There are various methods of how one can do this. So I think the first time, to my knowledge, that something like this was done was by Ben Withers using Padé approximants. You can do this. So we developed a method using this Darboux Puiseux theorem kind of mixture. And let me just give you an example. So of course, typically you don't have an infinite series of all the corrections, right? So the question is, can you develop a numerical algorithm to do this in practice? And the answer is yes. So let's take diffusion in ADS4, okay? ADS4 CFT3. So this is what is called the theory of M2 branes. So the general picture is as follows. So you start here from hydro, and we took 300 terms. And from that, we were able to find the dispersion relation of the next mode to 12 orders in the expansion. So it's about an order of magnitude reduction in precision, okay? But in principle, you can do it. So then, just to show proof of principle, we recomputed the other terms of the first dispersion relation here, and then we analytically continued there to the next one, and then found the second dispersion relation. And again, it's kind of funny. If you have 300 coefficients, you go down to, again, 12 reliable ones. I don't know why it goes from 300 to 12, but I think it's what is more telling than 12 is that there's a roughly sort of an order of magnitude reduction in the precision. So you can see that, if you really wanted to reconstruct the entire spectrum of these quasi-normal modes, you need lots and lots and lots of coefficients, okay? But it can be done. We have an algorithm that works numerically, so this can be done. So, okay, so why is this interesting? Well, it's conceptually interesting, I think, and instructive, practically not particularly useful. But the point that I'm trying to make is if you know the dispersion relation of one of the modes, then by just doing analytic continuations, you can find the dispersion relations of all of the other modes, okay? That's the statement. So in principle, if you know the full gradient expansion hydro theory with all the coefficients, these coefficients contain the message of all the other modes. And of course, ideologically, this is the same as these previous position space resurgence statements and things like that. Yeah, so go on. Yeah. Well, I mean, we did this at infinite coupling, so there are no other branches. If there are other, yeah, you would, because all of those, as I said, have non-trivial interactions. So they come wherever the poles collide. You can do this at the locations where the poles collide. So you would be able to do this, yeah. Yeah, absolutely. Yeah, that would be nice, yeah. Yeah, if you knew the whole, yeah, if you knew the whole Wilsonian term with all the Wilsonian coefficients, something like this, yeah. So here we can just do it explicitly. That's why, again, holography is nice, right? Because you can compute these coefficients numerically. Even I can do this. I'm not very good at numerics. You can just do it. It's very nice, yeah. Anyway, so first statement, hydro knows about all the other modes, or in fact, any one mode knows about all the other modes, okay? You could go from any direction. So that's statement number one. And now, statement number two, and the statement here is also that we have an algorithm that does this. Statement number two is, an even more sort of vast simplification, I think, of the complexity of how you can calculate this kind of stuff. So before, if you remember, I told you that in order to find holographic spectra, you need to solve partial differential equations, or in simple cases, ordinary differential equations. So actually, one can even turn this reconstruction problem, schematic reconstruction problem, into a purely set of algebraic equations. So there's a special role of what is called nowadays pole skipping in all of this stuff. So for those of you who have never heard of pole skipping, so pole skipping we originally found because of some bizarre connection between sound modes and quantum chaos. Okay, this goes to the study of quantum chaos in holography, but it won't matter too much for what I'm going to say. So the statement is as follows. So my dispersion relation, let's say of sound mode or diffusive mode, whatever, is an infinite series. It's an infinite series. And this infinite series, when you evaluate it at a certain specific imaginary value of momentum, has a following property. At this imaginary momentum, Q, which I can call I times lambda over V, why not? This will always equal to I times lambda, where lambda is this holographic maximal Lyapunov exponent that tells you about how chaos propagates in these large N models with a holographic dual. Okay, I don't have time to go into details of this. So in these simplified holographic large N theories, this is always 2 pi times the temperature. So it's exactly, so this happens on the wrong side of the imaginary axis at the first Matsubara frequency, okay? It's okay, because here my Q is imaginary, so the stability doesn't suffer from any problems. So why is this called a pole skipping? It's because there's a special thing that happens to the correlation function. if I evaluate my dispersion relation, anywhere along the trajectory of omega as a function of q, of course I have a pole in the correlation function, I have a 0. So at some special points in this complexified q space, there will be a 0 residue to this pole. So this is called pole skipping now, because at this special point, the correlation function is exactly 0 over 0. Now, so the correlation function is still regular, but the value of the correlator depends on how you approach it in the omega q space. Okay? So the pole has a 0 residue. That's why it's called pole skipping. And actually, there was just a very nice paper 2 weeks ago that finally proved why this is exactly the same as computing quantum chaos, why this is also the same as what people call the spread of entanglement in holography. There's a very nice paper from the Cornell group that proved this. I don't have time to discuss this, but basically the reason why this is so extremely robust is because of a new feature of gravity. And it's to do with a certain triviality of Einstein equation, and in fact, any wave equation at the horizon, okay? Again, the detail's not so important, but from the field theory point of view, there's always going to be an infinite number of such points where there's a 0 over 0 in the correlator, and they always happen in frequency at multiples of Matsubara. So minus 2 pi tin, there's an infinite number of them for n greater or equal to 0. There's one special one at n is equal to -1, and this special one tells you about the spread of quantum chaos in your theory. That's the one that we originally found. But okay, this is the statement. So now, what does this have to do with anything? Let me go back to my diffusive model. This is my dispersion relation. I mean, a diffusive model. I mean, I'm doing holography, so there's a diffusive mode plus an infinite number of quasi-normal modes. The Christmas tree. Yeah. Light-like spec. Sorry? Not that I know of. No. These are not on the light cone anywhere. No. 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 Not to my knowledge. No. Okay, so this is an infinite series, right? So what will happen in these holographic models? You will have this diffusive mode, and as a function of q, if you increase momentum, it will just go down, okay? The dispersion relation goes up, this mode goes down. So as it goes down, it of course crosses all of the multiples of Matsubara frequencies, minus 2 pi I Tn, okay? Now, what one can notice in only the 4-dimensional gravity calculation, which is dual to CFT3, is that you can find these values of frequencies analytically. You can find them analytically, and actually from this you can determine that the dispersion relation of the diffusive mode as q goes to infinity will go as q to the 4, which is a little bit bizarre, and it looks like it's violating something, but it's not violating anything, because actually the residue of it goes to 0. So it's a bit funny, but you can find the asymptotics of the series at q going to infinity from pole skipping. Because you see, these pole skipping points come closer and closer together in some sense, so they kind of sort of smooth out, okay, along the dispersion relation. Doesn't matter. So my claim here, another thing that maybe I didn't stress enough, you can compute these pole skipping points, so the special locations of where this mode is from a purely local horizon analysis by just doing algebraic manipulations. Anyway, so my statement now, the second statement, is that actually, if you only know where the mode is at these isolated points, in some way, you can figure out the entire dispersion relation of the hydrodynamic mode as it goes through. That's the claim. And then, of course, once you know the hydrodynamic dispersion relation, then you can, in principle, find everything else from it. So how do you do this? Well, this is a fancy interpolation problem, okay? So, I mean, it sounds a little bit crazy, but you have a function that goes through an infinite number of predetermined positions. Can you determine the function? Of course, the answer is no. How on earth are you supposed to do this? Any number of functions can do all sorts of things, unless you have special analytic properties of the function, which here you don't. Not seemingly, you don't have any special analytic properties. So there wasn't such a very obvious way of how to do this, but we found a way of actually doing this, and the trick is yet another analytic continuation, which I think is also interesting for QFT. So basically, you need to put this theory in d dimensions and go to infinity, and expand around infinity. Now, this is a sort of it's a well-known trick for various things. So the reason why this is a nice limit is, for example, because things like Newtonian and Coulomb potentials, when d goes to infinity, become ultra-localized. So typically in the infinite d limit, you can solve things exactly. And then you develop perturbation theory around 1 over d. This is, for example, a trick. There's this bizarre popular science paper, I think it was published in Science somewhere, I don't know if people know this, written by Witten, where he argues that you can use this method to solve the helium, to find the ground state of the helium atom in Schrodinger equation, analytically, in 1 over d expansion. And you can, actually. People have done this. Yeah? What does that mean? You mean in some... This is just gravity in high number of dimensions. Nothing is unstable. I don't know. I don't know what that means, but I can tell you that it works. You can just compute any state of hydrogen in this expansion, and it just works. It gives you the right result. You can compute the Yukawa potential. There are these. I give this actually to my students as like an assignment for a bachelor's project. Of what? Mm-hmm. There's no uncertainty principle here. This is just classical wave equations. A Schrodinger equation is a classical wave equation with some i's in there. I mean, from this point of view. You know, it's a fancy diffusion equation. You just, I can tell you, yeah, it's not, I mean, there are reviews, it's very nice. There are reviews written about this. You can, so for example, what is not clear is the convergence of this. Maybe in some of your cases, this will blow up at certain d. That could be. That may be. Yeah, so basically, we can do exactly this, okay? And what is nice, the reason why you can solve this problem is because in any number of dimensions, even in infinite d, there's still an infinite number of pole skipping points. However, what is special is that the hydrodynamic series truncates, okay? When you go to infinite number of dimensions, the hydrodynamic series truncates at second order. It's just 0 beyond. And then at higher and higher orders in 1 over d, you can write down the hydro series as a double expansion. So it's a double expansion in momentum q and 1 over the dimension. And now, what you're interpolating is a finite series to an infinite number of points, which of course you can do, okay? So you can do this. You can find some kind of generating functional order by order, and you can compute, in principle, all of the hydrodynamic coefficients in d number of dimensions by using only pole skipping points. So we show how to do this. These coefficients that come in have some very nice, seemingly perhaps mirror symmetry between calculations of hydro and pole skipping. I don't have time to do this, to go into the details. There's some various analytic continuations involved, but one can do this, okay? And we show explicit examples of how to do that. So just generically, the statement now would be the following. Well, you can find the hydrodynamic modes, right? So you find this in the series of 1 over d, and then you evaluate at any number of dimensions. And actually, regarding convergence, it's kind of cute. It works for dimensions bigger than 2, which is very good because there's no dimension, and there's no diffusion, and d is equal to 2. So the convergence of the 1 over d series knows the dimension where diffusion still exists. That's kind of nice. Yeah. Yeah. Mm-hmm. Yeah. Can you try to just solve it there if it's trivial and then do a perturbation theory? Like for helium or like for hydrogen? Yeah. Mm-hmm. Yeah. 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 Okay. Yeah. So I think the way people think about this large dimension expansion is like 1/n, kind of 1/n. You know, things are sort of semi-classical, trivial, and large n, and then you develop a series in 1/n. So yeah, I think it's, yeah. I mean, in these cases, it just works. Now, you know, if it generically works for every problem of physics in the world, I have no idea. Probably not. So I think just this part of the statement, right? What is nice, I think, is the following. So you can, in principle, so all of the information about the correlation function is encoded purely at the horizon in some, you know, very infrared limit of your, so this is more of a holographic statement, but everything can be found from just the behavior of this hydrodynamic mode. So one reason conceptually why this is nice is because it reduces the calculation of spectra. Well, holography first reduces it from an infinite number of Feynman diagrams to an ODE. And with this, you reduce from ODE to a set of algebraic equations. Now, once you have all the poles, then you can use a very nice recent result from the CERN group, which tells you that if you know all the poles for meromorphic functions that behave in this way, you can also get the full correlator up to one function of Q. So the point is that all the residues of the poles can also be determined from the poles themselves. Okay? There's a recent paper, 2023. This now goes by the name of thermal product formula around Sasha Zheboyedov and collaborators from CERN. So, okay, so now one can use all of this stuff to finally come to the title of my talk, which is the spectral duality relation. And again, the details won't be very important, but what I want to show you is I think very nice relation between spectra. So this is done in collaboration with my PhD student in Edinburgh, Mile Verbica, who's doing extremely great work. So we had one paper out already, and now we're finishing 2 more papers on this to show various applicability of these kinds of constraints. So, you know, it goes under the general umbrella of these spectra are extremely tightly constrained. So originally, the way we found this, so let's go to ADS4 again. Okay, ADS4 has a dual 3-dimensional conformal field theory. In these theories, you have an even channel and an odd channel of perturbations. So the even channel are the sound modes, okay, the longitudinal perturbations. Transverse perturbations are odd. This is even odd is this language of how they transform under the Z2. It doesn't matter. So there's a sound channel and there's a shear channel which has the diffusive pole. Okay, so there's a diffusive pole like I showed you with all the Christmas trees, and there's a sound channel with a pair of real poles and the Christmas tree. Okay, that's the general picture. So, okay, so the statement is as follows. So in 4-dimensional gravity, or CFT3, something special is going on. So these theories have dualities. There are many versions of the same thing. You can call this the S duality or the particle vortex duality in field theory. On the gravity side, you can call this the Chandrasekhar duality or the Darboux duality or the electromagnetic duality or the something found from the Penrose-Newman formalism duality. They're all exactly the same. All of this is exactly the same. So in all of these theories, what happens is that at finite temperature, okay, so this is finite temperature, the correlators in the 2-channel obey a special duality relation. So generically, for all these kinds of correlators of conserved operators or not even conserved operators, you will get the correlator. These are retarded correlators. So G plus times G minus is some function. Omega, which is just the frequency, divided by something special, omega squared star. So omega star, you can find analytically, and this corresponds to what in the old language of gravity are called algebraically special frequencies. And these algebraically special frequencies are actually a subset of pole skipping frequencies. So this is related to pole skipping. So, you know, all of these constraints, effectively you can think of as coming from pole skipping. These are exactly the frequencies of where the pole goes through the pole skipping points, okay? On this imaginary axis that I was showing you. There's a one-to-one correspondence. Yeah, 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 exactly. With all the hydro modes and the Christmas trees and everything. It's like this omega equals to some number times q to the 4. It's that thing that I showed you. So it's the dispersion relation of, it's like an interpolation of pole skipping points along the imaginary axis. That's what it is. Yeah? And you can find this. There are, again, 15 different ways of computing this or stating this. Petrov type D solutions, things with null shear geodesics, or Robinson-Trautmann solutions in geo. There are many things that are the same. Anyway, so you can find this from gravity. There's a special limit of this, which we call the self-dual limit. It's, you know, in the parameter space of temperature and chemical potentials where this omega star goes to 0, okay? And then in that special cases, you have G plus G minus is equal to -1, and this has been studied before. For example, this was a paper by Pavel with Sachdev, where they were using this relation in exactly this theory to find conductivities, right? Yeah. Yeah, it's the JJ. So the JJ correlator has the special property that for it, this omega star goes to infinity. So it's the special self-dual limit of the general picture, okay? It's special for JJ correlators at 0 chemical potential. Okay, so we can now take the mixed quasi-normal modes. So omega plus are the quasi-normal modes in the sound channel. Omega minus are the quasi-normal modes in the minus channel. And omega star is this thing that you find from gravity. It's the only input from gravity. You can form the following infinite product, and we can prove using general properties of meromorphic functions, and in particular this thermal product formula of Zhiboyedov and collaborators, that the following universal relation for all such cases is true. So this thing, this infinite product, this is K is equal to Q. I don't know where I got, okay, so K is equal to Q. So it helps in the proof, yeah. Yeah, so so in order to prove all these convergences, you use this kind of Hadamard adaptation of Weierstrass, exactly. So it's like a Weierstrassian product, yeah. To prove convergence of these things, and one has to be very careful with convergence of these products, but it's to do with that, yeah, exactly. So this thing, I think it's extremely striking. So this thing is, so the odd part in frequency is completely constrained. So S of omega minus S of minus omega, it's very far from obvious why this should be true, is always equal to 2i lambda of k. Lambda is one function which does not depend on omega, okay, times sinh beta omega over 2. It's always true. So for example, you could then even, if you know all the quasi-normal modes, you can also express this lambda as a sum of inverse dispersion relations of all the quasi-normal modes. You can do this. So the point is that the right-hand side has a completely constrained dependence on omega, okay? Even though this looks like it could be some insane function of omega, it's not. For all of the theories, anything in 4D gravity, anything with this duality, it's always just sinh beta omega over 2. So actually, this has a lot of consequences. In particular, one can derive infinite numbers of constraints on generic spectra, okay? These are some constraints written in terms of the sums of different powers of quasi-normal modes. It doesn't really matter. You can evaluate them at Matsubara frequencies and so on. This is not so important. The point is that you can play with this. Okay, so what we did originally, so this JJ correlator that I was discussing with Pavel is self-dual. So this is the special case where the right-hand side is equal to -1. And for example, just using this, you can prove that as momentum goes to 0, all of the poles must go to the imaginary axis and to the Matsubara frequencies. Okay, you can just show this, that it cannot be any other way. For example, if you go to the energy momentum correlator, then omega is exactly this, what I told you. It goes as q to the 4. Here you can prove various things. So you can see, so this is a picture of how this function S minus S looks when you're adding higher and higher quasi-normal modes. At first, it looks like something. So basically, everything goes to a cinch. This is done for imaginary. If omega, so as you add more and more and more quasi-normal modes into this product, everything eventually goes to a sign. Okay? So for example, one thing that you can get just from this constraint between spectra is that the diffusion constant divided by the attenuation rate of hydra must be equal to 2, which is always true in 3 dimensions. It's kind of interesting. You don't assume the hydra expansion, it just comes out, for example, okay? So it kind of knows certain features about the hydrodynamic effective theory. Huh? Gamma? Oh, it's something that depends on temperature. Oh, it's, so sound mode, omega equals to Vk minus I gamma k squared. And if you just use the spectral duality formula, you plug in the series expansion for diffusion and sound, you find that D and gamma must be related in this way with a factor of 2, which you also get from the hydra effective theory. So it comes out. No, electromagnetic, no, this is just TT, this is just graviton. Mu is 0. It's shear diffusion, momentum diffusion. Momentum diffusion. Yeah, exactly. And you can do these things for Reisner-Nordstrom things and so on. Okay, so all I want to say is that it's kind of, I find it very remarkable that indeed, whenever you have such relations between Green's functions and just the assumption that the Green's functions are meromorphic, you get insane amounts of constraints. So this was our first paper, and I'll just sort of in 2 minutes tell you about the recent results. So you can use this to go sort of even further, and it's simplest to constrain yourself to relations like this. Okay, just take this self-dual limit, whatever. So there are 2 correlation functions, whatever, G plus G minus. They don't have to be the sound and the shear channel. As long as you can show that they have this relation, or then you can form this product, and this product will always obey this kind of a constraint equation. And one thing you can prove, which we managed to prove now, which we didn't quite have fully done in the first paper, is that actually by just knowing the spectrum of one of them, you can determine the spectrum of the other one, okay? It comes out completely. So you only need to know the spectrum, the quasi-normal modes of the shear channel, and you will get all these quasi-normal modes of the sound channel by doing some very complicated algebraic resummations of things, okay? But it's all completely constrained. And it's all coming down to this duality. So this we can do. Another quite cute thing is the following. Let's forget holography. Let's just have a meromorphic correlator, okay? G. This equation is trivially obeyed by G times G to the minus 1 is equal to minus 1, yeah? Minus G, G minus 1 is equal to minus 1. So what are poles of G? The poles of G are the poles of G. What are the poles of G minus 1? It's the zeros of G to the minus 1. So the spectral duality relation tells you that if you know the poles, you know the zeros. And the locations of the poles are constrained by the zeros. So for example, you can prove this statement that whenever you have a pole, there must be a zero in between. And in fact, you can show that for any disk in the complex omega plane, the density of poles and zeros must be equal. It's all completely constrained, okay? So, okay, fine, you can again form this product, and it will obey this equation for any correlator, as long as the thermal product formula is true. And for example, you can get the residues, not only the zeros, but also the residues of the poles from some kind of a product formula, again, okay? Now, just as a last thing, this also applies to just large N field theories. Let's throw holography away. So in large N field theories, you have, let's say, some conformal field theory. Okay, so you have a conformal field theory with some operator. You can deform this field theory by adding a double trace deformation. Okay, this is an old story, goes back to various papers by Klebanov, Gupser, and various other people. I don't want to offend anyone. So this is a double trace deformation of your partition function. So it's generically true for such things that in the large N limit, this correlation function as a function of the double trace coupling F will behave in this following way. Once this is true, we can prove that a correlator at F1, whatever the coupling, times some junk, times the correlator at F2 times some similar junk is equal to -1. As soon as this is true, it means that from the correlator at any coupling, you can get the correlator at any other coupling. Okay? Because you can use the spectral duality relation, you can get poles of one from the other, then you can get the residues and you can get the zeros. You can get everything. Okay? So for example, a particular, well, because otherwise, you know, you have corrections when you compute this. This is not true. These relations aren't true. Yeah, all of this is true for large N. Yeah, so one very nice example that I think resonates with holographers is that, you know, you have a connection along this RG flow between a UV and an IR CFT. That's a very explicit. So you start from a UV CFT, which usually in the holographic language, you would use this alternative von Neumann boundary conditions. Then you have a double trace RG flow to an infrared fixed point, which is the Dirichlet boundary condition. So the conformal dimensions, at least for scalars, here are related in this way by this duality. So this is all sort of, one is a Legendre transform of the other one. The couplings are related in this way, and the correlation functions are related in this way. So you can take the coupling to extremes, and you can show that the correlator at the UV fixed point times the correlator at the IR fixed point is equal to -1. So again, you can use the spectral duality relation and all of this machinery to compute the correlator at the UV fixed point from the correlator in the IR fixed point, or vice versa. Okay? Yeah. Good. And in fact, because what is really going on here is just a Legendre transform, you can do the same thing. So as long as you have any correlator in any theory that is related by a Legendre transform to a correlator in the other theory, all of the same stuff applies, as long as you assume that the correlators are meromorphic. Okay, that there are no cuts. If they're cuts, then I don't know what happens to all these theorems. But as long as they're cuts, you can essentially do everything. Okay, from one to another and all these kinds of manipulations. This is just some picture of how they look like worms. These are the flows of quasi-normal modes as you tune F from infrared to the ultraviolet and so on. So you can start in the ultraviolet, use equations to find the spectrum anywhere along the RG flow, then dualize, go to the infrared, and so on. Okay? They're infinitely tightly constrained, all these things. Good. This is what I wanted to talk about. So QFTs and gravity, in this short summary, are very interesting and very powerful, okay? Because there's a lot of these mathematical structures that I think we can exploit, okay? And that people have sort of been learning. There's, you know, there's an entire other program of the S matrix analyticity, things like this, bootstrap. All of these are, you know, exploiting these very stringent mathematical structures in QFTs. And in particular, I think what I tried to show you today was that these large classes of large N theories, even at finite temperature, which would be normally extremely difficult to treat from a QFT, thanks to the analyticity of holography and all of these properties, we can find infinitely stringent constraints on all of these spectra, okay? They're extremely tightly bound. You cannot just have just about anything, okay? So, you know, even if you don't care about QFT, then all of this just applies to gravity, to black holes, to spectral black holes, and various things, okay? And yeah, this is very nice, especially from gravity, from holography. The question, as always, is raised, what about realistic QFTs? I don't know, we'll see, okay? So that's all from me today. Thank you very much. Not too bad. It's quite unexpected to me, because yeah, yeah. No, no. You can add scalars, you can add vectors. Yeah. No, we have all these examples. We do it for Reisner-Nordstrom at finite chemical potential. You can add scalar fields, you can add axions. It works for everything. Yeah, everything. Absolutely. We have tons of examples. Yeah. BTZ, you can just plug in BTZ and so the statement is following. Should I be quoting D's in terms of QFT or gravity? Okay. D spatial. Whoa, that's the hardest. so D spatial equals to 2 is extremely constrained by all of this because of S duality and particle vortex duality. So there it works because of that. And then it works generically in any D in the large N limit because various things are Legendre transforms of each other. And it just so happens. So for example, you could even do MHD Legendre transformed to non-MHD. It's just, you know, the machinery works for any dimension, for any operator. So yes, so D is equal to 2 is special because of S duality. That was the only reason why we found it at first. And so that is special. But then, you know, for these large N theories, it works in any dimension. And in any dimension in the large N limit, I guess one statement would be that for any correlator, the zeros and poles are constrained in this way. Yeah, so I don't, yeah. As long as they're meromorphic. What happens with cuts, I don't know. Again, you know. So maybe it's all, yeah, I don't know. You don't need gravity. Just Maxwell's fine. You need a horizon. Yeah. You need a wave equation in a space with a horizon. That's what you need. Yeah, this is special, yeah. Yes. That's right. Yeah. Yeah. So we're writing one paper that has nothing to do with holography. Nothing to do with holography. It's a statement about meromorphic functions. Because meromorphic functions are tightly constrained. Okay? Basically what is going on is that these correlators have power law behavior at infinity. So as long as a meromorphic function has power law behavior at infinity, it has isolated poles and zeros, there's a ton of theorems you can prove. Yeah. It's just very constrained. And also this thermal product formula of the CERN people, you know, came from that. So it started with them noticing that the Whiteman function, so Whiteman function, the symmetric correlator in these kinds of theories has no zeros. That was their original statement. There are only poles, no zeros. And from that, you can just go crazy. Prove everything. Yeah. It does look like that, I know. There's a cinch. Yeah, I don't know. I agree. Not that I know of. Yeah. Yeah, so this lambda is one function of k. That's not a function of omega. That's the one thing you need to find. Yeah. But you can find it from the quasi-normal modes again, so. I mean, it's a thermal state. Everything has to do, I don't know. Yes and no, which is restating the fact that I don't know. But, you know, all of the cuts in the zero temp, yeah, sure. You know, people prove the MSS bound on Lyapunov exponent, and then someone comes out, oh, but this is just fluctuation dissipation theorem. So yes, I think it would be nice to see. I mean, if one can prove this just using fluctuation dissipation theorem, that would be, yeah. I think it's absolutely interesting. I just don't know. Yeah, so I should maybe point out, so for example, you can try to do the same things so there's a funny thing here. So it's some kind of conservation of evil. So if you don't do asymptotic anti-de Sitter space, you could look at quasi-normal modes in asymptotically flat spaces because we seem to not live in ADS, right? And you can ask, what does this say about flat space? And the answer is 0. So what this thing tells you is the departure of one spectrum from the other. And actually in flat space, I don't know if people appreciate this, but in asymptotically flat space, in 4D, in our world, the spectra of shear and sound perturbations are the same. This is called isospectrality. of the quasi-normal modes. So there, this just gives you 0 on the right-hand side. So this is kind of, you know, so from the point of view of gravity, this works extremely well in ADS, not so well in, it's kind of tautological in flat space. To be seen for the sitter, unclear, but anyway, so I maybe wanted to point this out, that you should really think of this as one spectrum from the other being completely constrained as you go. So if they lie on top of each other, like in asymptotically flat gravity in 4D, where there's a property called isospectrality, then this just gives you 0. And it's the fact that it's S minus S of minus, so it's the odd part, okay? Just wanted to mention this. Kind of. No, it doesn't. It doesn't. But it does give you that the spectra are the same in asymptotically flat spaces. Yeah, I agree. I agree. Not really, yeah. I mean, it's defined in terms of poles. So I think really, I mean, of course, everyone knew before, right? Pavel, your papers, everyone knew that there were duality relations between correlators. What is new is that you can you can do all of this just from the poles, okay? Because you couldn't do this before, because you know you could have a pole canceling a 0 if you don't know where is one, where is the other, what is going on. So the new information is coming from the fact that all of the information is in the poles. Yeah, so I think, which is why so we kind of wanted it to be in terms of poles, not in terms of G, because G's are already, you know, G plus G minus equals to something. If you know G plus, I mean, you just divide and you know G minus. Maybe, yeah. Which is probably related to the fluctuation dissipation theorem, which is probably related to the Sinch. Probably. I'm sure this is all a web of consistent statements. Yeah, exactly. Somehow. Yeah, no, yeah, I agree. Thank you.